Hey, what's up guys? Welcome to the third lesson on building our YouTube game engine from scratch. This lesson is going to focus on implementing an initial renderer. We're going to render using Vulkan. Now, I will preface this with the fact that I am not the best or even close to the best. I am not very experienced with Vulkan and rendering in general. So this is as much of a learning experience for me as it is for you, minus the fact that I've actually done a lot of this in my own personal version of what we're building. Once again, properly cite my sources. We are going to be following loosely some of the stuff that we're doing that is described on vkguide.dev, which is, in my opinion, the best written Vulkan tutorial that you can really find for doing stuff a little bit more sane without having to do all the thousands of lines of code that you would normally need. So that being said, we're going to get through this first part today, initialization and render loop, which in the end will give us a screen that is, I believe, flashing blue. Yeah, we should see a flashing blue screen. The next lesson, I haven't decided yet. We're either going to continue on with number 2 here, or we're going to go back out and do some more engine framework stuff to then come back here and do this in a slightly different way. So I've got this resource open on the side. I've also got my personal project here, which actually just quickly I'll show you what this does. I'm going to need to grab something quickly for you to see. So as you can see, that this is actually rendering into my Valve index, and this is what we're actually going to be working towards in the end here. And it's a little broken right now, but you can also move around, look around, and this is what we're building towards. So if you're excited for that, stay tuned in on this series. We're going to show you step by step how to get to pretty much exactly this, minus the few differences between what I'm building and what you're probably going to want to do. So if you're interested in VR, I'm going to show you how to make this a VR renderer. But if you're not, we're going to take it up to the point where it becomes a VR renderer, and you can basically just skip that lesson if you don't want VR. But eventually I'm going to add a toggle to turn VR on and off, and then you'll have an engine that supports both. Okay, so the first thing that we're going to have to do is install the Vulkan SDK. So you can go to lunarg.com, which is currently the only, as far as I know, SDK for Vulkan that you'll find for desktop platforms anyway. Click the download button, you'll go here, click whichever version you have, and install the SDK you want. When you launch the installer, it's going to put it in most likely a default location, usually under like C Vulkan SDK. I don't know how it's going to be done for the other platforms, but you should know how your platform works. Hit the install button, let it install. Doesn't take too long. There we go. All right. When you're done installing the SDK, what you're going to have is, if you go inside your environment variables, you're going to see that it's set Vulkan SDK path and Vulkan SDK, these two environment variables, as system variables. If it didn't do that for whatever system you're running on, just make sure that you're going to want to put it inside your bash profile, probably in macOS or Linux. Once that's done, once you finish your install, if you had any editors open, you're going to want to make sure to fully close them down. I've already done so off screen to make sure that it picks up those new environment variables. With those environment variables in place, what we want to do is add one more dependency. Now, as I mentioned before, I like vkguide because it introduced me to a library called VK Bootstrap. So let's Google that. And I believe it's this one here, VK Bootstrap. And what VK Bootstrap does is it handles a lot of the boilerplate stuff you're going to be doing with every Vulkan application for you. So we're going to grab this. Oops, wrong button. We're going to grab this and we are going to add it as a submodule to our project. So inside our terminal here, and this is just a terminal with the YouTube project open, we're going to want to go into the engine because it's an engine dependency. So cd external, cd engine, and we're in here. So we're going to go git submodule add, and we're going to, let's try that again because I think I took it off of my, so git submodule add bootstrap as external /vk bootstrap, and that will add it as a submodule. So with both Vulkan downloaded and VK bootstrap, we can now add it to our CMake list for our engine. So make sure you're inside your engine folder, and we're in VK bootstrap. We're in our CMake list here now. Now we want to add VK bootstrap. So again, it's the same pattern. We're going to add subdirectory external /VK bootstrap. Then inside our include directories, we are going to, so it's going to be in our private, we're going to have VK bootstrap. Let's put it after glfw. VK bootstrap. And then in our link libraries, we will also put VK bootstrap. All right. Now, if we reload this, it should properly reload our CMake project. There we go. CMake written and everything's fine so far. Now, the next step we need is we're going to need to include our Vulkan SDK. So that is actually fairly simple. What we're going to do is we are going to call a function after our subdirectories. We're going to find some packages. We're going to just put here library find functions, and we're going to find a find package Vulkan, and it's required. What that's going to do, it's going to create a few CMake environment variables. So let's look at so let's find package Vulkan. Find Vulkan. You'll see here that it creates, it defines a few variables. It finds the library Vulkan found, include directories and libraries. Now we're going to assume that found is true because required is true. And then we're going to need these include dirs and these libraries, right? Now, simple enough. Now we're going to put it inside public, but in the end, we're actually probably going to want it down here. But we're going to put it in public for now, just to to prevent some issues in the future, which we might run into. If not, I might have fixed the issues by the time we get to them, and if that's the case, we'll move it down. Actually, you know what? Let's move it down to force us to fix them. So we are going to take here, we're going to put Vulkan include dirs. And that was just this one here. Now we need Vulkan libraries. We can copy that. And inside our target link libraries here, Vulkan, we can just paste it, Vulkan libraries. Now, if we reload those changes, we should be able to load that properly, and everything builds fine. Now let's just quickly add some Vulkan stuff to the project. Add some Vulkan stuff to the project so that we can ensure that it's linking properly. So the first thing that we're going to need to do is upgrade our GLFW window here, our multi-platform window. We're going to need to make sure that this is Vulkan, driven by Vulkan, right? The most simple way to do this is at the top here in multi-platform window. We're going to add a special define that's specifically for GLFW called GLFW include Vulkan. And then glfw3, where am I including that? Probably in here. So since we're including it here, we'll actually just move this define into up here just to be consistent. So we'll define glfw include Vulkan. And what that will do, that will include Vulkan. So in theory, this should build okay. And you'll see now it builds okay. And now if I specifically include Vulkan/Vulkan.h, you see it shows up. And if we build that, everything seems to work okay. Now there's probably a couple of things we need to do inside our glfw with our glfw window. Okay, so before we open the window, what we're going to need to do is set a few window hints. Now, right now, let's just launch our window and see what we can do with it. And we're going to do a few things just for now. So here you'll notice that we can resize the window, and you'll notice it stays white. That's going to be a problem when we start rendering Vulkan stuff, and it's a problem we'll deal with later. But basically the idea is every time we resize the window, we need to recalculate and rebuild all of our pipelines, which will, at least initially, crash some of our programs. So to fix that, we're going to create one window hint, glfw window hint, glfw resizable, glfw false. And that will make it so that we can't resize our window. So let's just run that again. And you'll see now that we can no longer resize our window, which is exactly what we want. The next window hint we're going to need, so glfw was initially created for, as the name implies, OpenGL. Now with Vulkan, we no longer use OpenGL, and we have to tell glfw that. And for that, we have a new, I don't know if it's a new window hint, but we have a window hint called glfw client API and glfw no API. And that's everything we need to do with our window to support Vulkan, in theory, for now. There's going to be more stuff that we need, but for now, let's go with that. So let's play that, and it should still open fine and should still run okay. So perfectly okay. Exit with 0. Now we get to the fun bit. The next thing we need to do is we need to define and provide a renderer, right? So there's gonna be, we're gonna do this a few pieces at a time, because I don't want to get this too complicated to begin with, right? Because this is intended to be a thorough but also informative introduction to creating game engine. So right now we have our platform, which provides our entry point and our window, which is all we have in our engine. The next thing we need is we actually need a renderer now, right? So now renderer doesn't really sit with platform, so we're going to create a new folder inside here, and we're going to call it render or rendering. And inside our rendering folder, we're going to create a new header file, and this one's going to be called renderer renderer.h. And we'll add that to the file, and we are going to reload our CMake project. Okay, so we got our renderer and pragma once, that's fine. Before we get too much further into it, one thing I do want to do, and what I meant to do, is we should be namespacing all of our stuff. So what I'm actually going to do is here, this is fine, but our game, we're going to wrap this in a namespace, and we're going to call this, let's call it Oz. Put it inside my own namespace. You can namespace it whatever you want. There we go. Now window also should be namespaced. Now this is going to cause some issues when we go to build, but we can fix it one step at a time. Renderer.h, same thing. We're going to add a namespace Oz. I don't know why it put a semicolon there. Okay, and service locator again, namespace Oz, There we go. Game, again, we want a namespace Oz that. Namespace Oz. Multi-platform window. Namespace Oz. Multi-platform window. Namespace Oz. And now I think that's all of them. And in here, we're going to get an error, right? We're going to do using namespace just because I don't feel like typing Oz over and over again. But in theory, you should probably be doing like Oz game, Oz create game. But we're just going to do it like this, just because I'm lazy. Now, in theory, this should work. Let's have what's the problem. Create game identifier not found. Oh, there we go. That should work now. No, maybe I need to specifically be explicit on this. Right, so for create game we'll need to be explicit, but that works. So we're back to where we were and everything's namespaced okay, and everything, hello YouTube game, everything works the way it was before. So let's go back to our renderer. So what does our renderer need for now? It's going to be provided by our service locator. And our service locator uses an init shutdown pattern. So what we could do, we could make an interface that has that all of our services have an init function that take an init function, provide an init function, a shutdown function. We could do that. We probably should do that, but we won't because I'm lazy. So what we're going to do instead is we're just going to be explicit about it. So first, we are going to create our class renderer. All right. What does our renderer class need? So our renderer class needs some public functions, and this is going to be a pure virtual class, just like all of our other services. So this is going to have a virtual void init equals 0. Now we're going to need this later, so I'm going to do it now. In here, there's going to be a struct that we're going to have that's going to be called struct renderer settings. And we're just going to leave this empty for now, but we're going to make our init function take our renderer settings. And then our renderer needs to shut down. So virtual void shutdown equals 0. This one probably doesn't need any arguments, so that's fine. And we also need a virtual void render frame. Now our render frame is actually going to take some stuff in the future, but we don't need it right now. Yeah, we don't need it right now. So we'll just leave it like this, and this is good. So with that out of the way, let's go to our service locator and we'll build out some of the stuff we need. So we have a provide function here. Now what we do want to do is we also want to have a way for some of them to provide and initialize their functions. So a renderer is pretty useless without some settings, right? So what we need to do is also initialize everything. So what we're going to do is we're going to say static inline void provide and initialize render and std any arg. And with that, we want to import our renderer. So that was just a shortcut, that thing. And we also want to import any. So let's include any. Now, standard any is a alternative to passing everything through void star, which is just basically taking away the type of the argument. But it's a safer form, which also allows us to cast it back safely to another type. So let's say now that we want to provide a renderer. So first, if renderer not equal null pointer, then we return. We're just not going to, we're not going to give them the ability to replace the renderer once it's already been initialized, because it'd be a pain to maintain. Renderer is not defined, so let's go define renderer. Same deal, static, inline, standard, unique pointer, renderer, and renderer equal null pointer. Now, the next thing we want to do is actually create our unique pointer and initialize it. So we are going to wrap it inside a unique pointer. So we're going to render equal standard unique pointer, render, and then we are going to say render init, and then standard anycast, render settings, arg. Now what this allows us to do is it allows us to, there's no reason why I did that. Okay, well, I mean, when I put this together the first time, when I was putting together my service locator, there was a reason why I used standard any for the arguments. Maybe it was just to homogenize the returns. We're gonna refactor this later, I think. I just had an idea, but I don't want to do it later. So for now, we actually don't need this standard any. There's no point. Might as well be explicit. And we can just do this, and then we don't need that. So that's what we're gonna do. There's no reason, at least there's no reason to be using standard any in this scenario. It was just something I was trying to do on my end before, and I didn't end up actually doing it, and that was just a leftover. So we're going to pass in renderer settings, and then every other one is going to have its own unique thing. And just to be consistent, we're going to do provide and initialize. And actually, we're just going to create our provide function. We're going to call these provide. Because provide and initialize is too much, so we're just going to do that. And if we need arguments to initialize, we'll pass it in. And our window doesn't have in it just has an open window, so that'll be fine. So we've got our provide function, which is all we need there. So now we need to actually create a concrete implementation of a renderer. So we're going to start with that. So let's go into our source folder, and we're going to create a new folder called Vulkan. Actually, we're going to create a new folder called rendering. Then we are going to create one new folder called Vulkan, and then we are going to call one new C++ class, and we're going to call it Vulkan Render. And we'll add that. My CLion settings automatically create a snake case because that's what I prefer, but you can use whatever file name convention you want. So our Vulkan renderer, before we go too much further, is going to inherit from renderer, and it's all going to be namespaced under Oz. There we go. And now we can reload this CMake project, and that will pull all the files in, and it's going to say expected class name. It should, yeah, and here we'll import the renderer, and there we go. And now if we build this, it should build okay. Good. Now we just need to override some functions. We'll just create dummies for now, and then we'll go into it later. So we'll finish it later. So void init renderer settings override void update shutdown override and void render frame override. All right, and we'll define those. Why did it do shutdown first? Let's undo that. Let's add the namespace Oz here, so that hopefully it will generate everything in, yeah, good. And now it's going to generate everything inside the namespace without prepending everything with Oz. Okay, so we've got some dummy functions. It's good. Everything's good to go. So now we want to actually provide that renderer. So we're going to finish scaffolding everything, and then we're going to actually start building the renderer itself. And I know lots of work so far. This is what happens when I have to explain everything along the way, but hopefully you appreciate the in-depthness of the explanation. So we've got this. Next thing we want to do is actually provide it. So in our game.cpp, you'll see here, initialize the renderer, is we're going to have to create a renderer settings, and there's nothing inside, but we can do that. That's fine. And we're going to say service locator, provide new Vulkan renderer and settings. And we will import that. Now it's doing that, but I think I can do this. No. Let's see. I don't like relative paths. So what can we do here? Rendering. Now why isn't it letting me do this? I expect that it should have let me do this. And that's not working. Right. So what we're going to add inside here is inside our private, we're actually going to add CMake current source dir /source, which will allow us privately to do exactly what I was trying to do. So if we go back into our Vulkan renderer.cpp, or game.cpp, this resolves itself because we made our source directory a private include directory. So that's all we added. We add CMake current source dir /source in our CMake lists, in our engine CMake lists. There we go, and that provides our Vulkan renderer. Now that will call our Vulkan renderer. It's going to call provide in here. And call provide, and it's going to initialize the renderer. Once that initializes, once it initializes the services here, it's going to get into our game loop, and inside here we are going to say service locator get. We don't have a get renderer, so we want to get renderer. So at the top here, we're going to static inline const standard unique pointer render and get renderer return renderer. There we go. Oh, and I forgot it. I put that semicolon at the wrong spot. Let's add some spaces to make it a little bit nicer. And let's go back to our game.cpp and we can now do it. So Vulkan service locator, get renderer, render frame. There we go. And that's how we're going to go into our renderer and render. So that is everything we need for scaffolding. And now we can actually go and start building our renderer. There's going to be one thing that we do need other than our Vulkan renderer.h here. Here is we're going to need one more header file. We're actually going to make a class. So the class itself, we can call whatever we want. We'll say call Vulkan Initializers. Actually, yeah, let's do this. Vulkan Initializers. Make it a class. Why not? We'll be more robust with stuff. Now, this Vulkan Initializer is going to be a static class. Everything inside is going to be static. Again, it's going to be inside our Oz namespace. And we are going to make everything public. And we can leave it like that for now. Let's add the namespace here. And then reload our CMake project. Now I just have that there because we're going to need to be going back and forth between here. And then we're going to be adding some stuff to this. So our renderer. So we've got public functions and we're going to have private functions. Sorry, one more file we're going to need here. And this is following the VK guide setup. You don't necessarily need to do this in this specific way, but we are going to do it in this specific way because it's kind of clean, so why not? So we're going to create a header file called vulkantypes.h, and we're going to add this. Now our vulkantypes.h is actually not going to be used for a while, but we're going to do that for now. So inside our Vulkan renderer, we're going to include all of those files. So we're going to include Vulkan initializers, we're going to include Vulkan types, and we also need the VK bootstrap that we talked about before, include VK bootstrap.h. And that's what we're going to be working with. And these can actually be inside our, these are going to be inside our, we'll leave them here. But they probably actually don't even need to be here. They can probably be inside our CPP file. So we'll put them in our CPP file. So we're going to define a macro with one more header file. Actually we're going to call it Vulkan utilities. Okay, and now Vulkan Utilities itself is going to be a class, but at the top of it we're going to define a macro, which is going to be handle validation of a lot of our Vulkan commands. So when we submit a command like create image or create buffer, we're going to need to verify the results. This will just make that easy for us. So first thing we're going to do is include IO stream. And the reason we're putting it inside this utilities file and not directly inside the renderer is because we will likely use this in other places as well. So we're going to using namespace std, which I don't like, but only in this one spot. And we were going to define our macro. So define vk check x, and we will add that here. So it's going to be do, put that on this line. And now we're going to add the end of lines, but we'll do this all after vk result equal x if why? I don't know why it uses namespace std, but then uses std here. I'm gonna remove that. And now std count detected Vulkan error std end line. And then after that, it calls abort. And then while 0. And that's our entire macro. So we will just add all of our end line comments, end line slashes, and that should do what we need to do. And along with that, we are going to include it at the top of our render as well in our CPP, include vk Vulkan utilities.h. Now it's probably going to complain because I need to reload my CMake project. Utilities. Okay. So, first thing we need, there's a few things that we need. So we are going to just make some functions, and then here, members. So again, private. Again, I like, as I mentioned before, I like separating functions from members, just to make it easier to look for stuff. But we're not going to deal with that for now. The first thing we're going to need is we're going to need a Vulkan instance. So to do that, we're actually going to need, at this point, we're going to need to import our Vulkan header. There we go. And we got our Vulkan header. We are going to need a debug messenger, vk debug utils messenger extension debug messenger. We are going to need a physical device. Yeah, we can keep in this thing core Vulkan. So we want to leave comments here because it's going to get fairly long eventually, and we're going to be doing refactoring in and out of this header file. So we want to make sure to be able to find what we need and put stuff roughly where they belong. We're going to need a physical device. We're going to call it physical device. We are going to need a regular device, which is just going to be called device, a logical device. So this is our logical device, and this is obviously a physical device. Now I'm not going to explain all of these core Vulkan concepts in detail. I'm going to show you how to put them all together and use them, but if you're curious at what these things are, again, I highly suggest you go to vulkantutorial.com or vkguide.dev. It will explain a lot of this stuff to you, and it'll make a lot more sense at that point. What I'm going to do here is I'm going to just use that code and, where appropriate, morph it so that we can use it inside of our application. Okay, and after the device, we need a Vulkan surface, and that's the thing we actually draw to. So vk surface khr surface. So with those defined, we will define our first function, and it's going to be void init Vulkan. And we're actually just, yeah, I'm gonna call this init core, because obviously we're initializing Vulkan because it's a Vulkan render. Let's generate that, and we will put this here inside of our init. We will say init core. Okay, one more thing that I forgot is in here, we're gonna need a place to store our render settings. So we'll just say here, we probably don't need a comment, but render settings. And usually you'll want to initialize stuff as they go. This will probably throw a bunch of warnings at some point that they're uninitialized, but it doesn't really matter. But at the same time, I don't like warnings, so you know what? Screw it. This one I'll initialize. These ones I won't. Okay, so let's go back into init. So the first thing we're going to do is save our renderer settings. Renderer settings equal settings. And then we'll init the core. So the first thing we're going to do is we're going to initialize the Vulkan instance. And now this is what is going to make building our application much more straightforward for these initial steps. So the first thing we're going to do is we're going to use our Vulkan bootstrap, and we're going to say we're going to create an instance builder, and it's going to be a builder. We want to make the instance, so we are going to go auto instance return. I don't like abbreviations so much, so instance we'll call it built instance equal builder dot set application app name. All right, so app name here, we're going to just say application name, but what we actually want here is this is going to be render settings dot application name. And we'll go add that now. So render settings, and we will say string application name. And you know what? Let's make this capital since it's public, and include string. There we go. And then inside our game.cpp, we are creating the settings, right? And we've got a window title here. What we're going to use, game run title. Okay, and what we're going to use is we're going to reuse this title as our application name. So initialize services, we've created the title, so inside here we'll go application name equal title. And that will have passed this all the way down. This will be a capital A, and I believe this needs a C string. There we go. When we have our application name. Next thing we need is, do we want validation layers? And of course, we always want validation layers. Always. We then need to specify the API version, which we're going to use let's just say 1.2.0. Even though we're not using any 1.2 features right now, I think we're going to just put 1.2.0 because we want to be relatively safe. And what we're going to do is we also need to use, we're going to output our validation errors to a default debug messenger that is provided by the Vulkan bootstrapper. And this is another place where it saves us code. We will be overriding this in the future, specifically when we get to OpenVR. You'll see why once we get there, but for today we can use that. And then finally we will build it. So now that the instance is built, what we need to do is builder instance. We'll call this builder instance. So now we have an instance that we've built. So let's say vkbuild instance, and this will be vkb instance equal builder instance dot value. And once we have that, we want to store the instance. So instance equal vkb instance dot instance, and debug messenger equal vkb instance dot debug messenger. And there we go. So now we are initializing Vulkan. Now, just to make sure that everything's working, let's build it now. And there's probably going to be some errors. And so hopefully it'll show us basically what we're looking for. vk layer screenshot.json, invalid layer manifest file. Yeah, it does. Okay, so this is an issue with the newer Vulkan API. Let's close SteamVR again. So for now, we can ignore this. Okay, so once the instance is built, we will need to get our. So this is at this point now we need to request our surface. Our Vulkan surface from GLFW. Request Vulkan surface. Well, this is going to be kind of annoying. So the Vulkan surface is handled by our window. How can I explain this? Our window shouldn't necessarily be aware that it's Vulkan requesting a surface. It might only be a Vulkan function. So well, let's look at our window here. So inside our window here, you'll see we have open window and update. Now what we need is a request window surface function, right? Which will give us our Vulkan surface. It's gonna be a little bit annoying to do this. So this is probably where we can use standard any. And now that I'm actually making this up as we go. So remember earlier where I said that I put Vulkan inside private, but in my personal project, it's in public. This is why it was in public, because I just called the Vulkan stuff directly in my personal project, but here we're gonna do it properly. So what we want to do is, first things first, is on our window class, we're gonna have to create the function. It's gonna be virtual full void request window surface, or it's draw surface. Now this is going to be a virtual function. Now we got to think of what this is going to take. All right, so let's start here and let's override that in our multi-platform window. Take this, go into our multi-platform window, and under here, let's close that. And we'll override that. Okay, so what does request draw service do? So what it's going to do, it's actually going to create a window surface in GLFW. So the actual call, it's going to GLFW create window surface here. And you see here, it requires a VK instance. So we'll say VK instance. It requires the window instance. It requires the window. So we have the window, so we can do that. The allocation callbacks, which let's just say allocation callbacks. And then we need an out pointer for a surface. So out pointer, so out surface, right? So let's assume that this is what we have. Now, to make sure that this is compatible with everything, what we could do is we could use a map of std any's and then just cast everything, right? In theory. So let's try doing that. Let's go back into our window. Let's include unordered map. Include unordered map. And then we will pass in a std unordered map of std. It would be std strings and std any. And we also need to include any. And then we can pass that same thing into our multi-platform window. Put this inside here. And then we will say args. And we will go here and also call it args. Okay, now what we're going to do is, it's generally, if you're doing something stupid like this, which it's not exactly stupid, but you get my point. If you're doing something like this, what you want to do is actually, we are going to make this an enum, and we'll make this an enum class. And let's just say enum class surface args. And we are going to create, let's say surface args. We are going to have instance. We are going to have allocators, and we are going to have out surface. And in here we can actually make this surface args. In here we can replace this with surface args. And in here we can replace it with surface args. And this should make it a lot more, a lot safer, a lot more straightforward to keep track of in the future. So what we want to do is we now want to extract what we need. Extract what we need. So what we're going to do is we're going to say vk instance. Actually, it's probably going to want me to do auto. Vk instance equal std anycast. And vk instance args and surface args instance. So we got one. Now let's just make sure that we have everything in the right format. Allocation callbacks is a pointer. So auto pointer allocation callbacks equal, again, std anycast. And what is this? This is a vk allocation callbacks. Vk allocation callbacks star args surface args allocators. And finally our out surface, which vk auto star, and this will be out surface equal std anycast vk surface khr star, and this will be args surface args out surface. All right. Now what we're going to do one more of is if this not equal vk success, and we are going to throw an error. Failed to create window surface. And we are actually going to wrap all of this into a try catch blocks. Can I do this? Catch by reference instead. No, screw it. I don't know how. I don't like errors. I don't personally like try catch blocks too much. Let me see what we catch. Here, let's do this. And then we will just count. Failed to create window surface arguments. Failed to cast window surface arguments. I don't know what the anycast error is. Let's see. Throw bad anycast. Throw bad anycast. Bad anycast. Okay. Bad anycast. E. Let's put this here. All right, that's E dot what? There we go. There we go. So now, if it fails a cast, it will catch it and display the error. So with that out of the way, that will create our draw surface, and now we can go back to our renderer, to our Vulkan renderer, and we can create the surface. Now, we can do surface locator, which again is not here. We'll import that, and we'll just, that did it automatically, but I'm just gonna double check my import. Good. Surface locator, get window, request draw surface. Now this is going to be instance, null pointer, and a pointer to our surface. And now this will actually be, we need to build our surface args. So std unordered map, surface args, std any surface args. I'm just curious to what instance. Yeah, I can do this. Cool. Surface args, allocators, null pointer, and surface args, out surface, and surface. And then we can take these surface arguments, put that there. And this requires one of those. There we go. And that, in theory, should create our surface. So let's build this, see if it builds. I always build after a few. I'm gonna hit play, see what it gives me. There we go. And we close that. Everything seems to be working okay. So the next thing we need to do is we are going to select our device. And yeah, we're going to create our device, select our device, and create a logical device. So we are going to select our physical device, select physical device. And what this is going to be, again, Vulkan Bootstrap will do this for us in a nice way. Be physical device selector, and VKB instance. So we're going to do selector, and we need a VKB physical device. And this will be, I'm just going to do VKB physical device equal selector dot set minimum version, which is going to be 1. Set surface, which is going to be our surface. Then it's going to be select not value. Then we will create our device, create the Vulkan device. So VKB device builder, and then again here we pass in our VKB physical device, and we build our device VKB device, VKB device, and again I think I can just do this device builder dot build dot value. And I'm going to do the same thing here, just for consistency. We're going to make this code nicer than the code I have. There we go. Select a VKB device, and there, done. That looks nicer. And this is one too far. There we go. All right. And then we will save it off. So device equal VKB device dot device physical device equal physical VKB physical device dot physical device. And we save those off. So what this is doing, just real quick, so we've created our instance. Then we create our Windows surface, and then we pick which GPU we're going to use. That's what the physical device is. It finds a GPU compatible with the surface we give it, and then we create a logical device, a device in memory, Vulkan device in memory using that GPU. And that's what this is doing. And we're saving the handles to them. Now, with that out of the way, the next thing we need to do is set up the Swapchain. So the Swapchain is basically how we flip between images on our window. So we usually render to a back buffer, and then once that back buffer is rendered, we push it to the window, and then we swap it with the buffer on the window, and then we render to the new back buffer, and then we swap, and that's called a Swapchain. It's a chain of images that you swap one after the other to create a smooth image. Usually, if you only have a front image, it will create tearing and a bunch of nonsense you don't want. So let's create our swap chain. So we're going to go back to our renderer.h, and we're going to add some more members. So that's core Vulkan. Now we're going to do swap chain stuff. So our swap chain, the first thing we need is a handle to our swap chain, vk swap chain khr, and we'll call this our swap chain. Then we also need our swap chain format, image format, vk swap chain vk format, and this will be swap chain image format. We will need a series of swap chain images. As I said, you're going to render to one image while one is being presented, swap them out, and then render to the image at the back. So this is going to be a std vector. So we're going to include vector up here. So this is going to be a std vector vk image swap chain images. And then we need, to be able to view images within Vulkan, you need image views, or VK image views. So usually you'll want one image view per image. You might want multiple image views per image, but in the case of the swap chain, we will want one image view per image. So swap chain image views. It's all the Swapchain members we need for now. And we will create one thing here, and we're actually going to Swapchain. So we're going to call it create, and here we're actually going to rename it. We're going to call it init core. We're not going to use snake case because we want to remain consistent. Sometimes I do that by accident. So with our new create Swapchain defined here, we will define it. We will grab a handle to it, and we will go to where we call init core. And right after init core, we're going to create our Swapchain. So our Swapchain. Again, this is more Vulkan bootstrap stuff that we could do. So we have VKB Swapchain builder, and you get the point. A lot of the Vulkan VK bootstrap functionality is builders for these various things. So Swapchain builder. A Swapchain builder, it takes our physical device, it takes our device, and it takes our surface. And it'll build a Swapchain on top of those things. So we are going to, again, VKB Swapchain. So you'll see that we create a Swapchain builder, and then we actually create the Swapchain. So VKB Swapchain equal Swapchain builder dot. We're going to use use default format selection. Now I think we can specify use format feature, use set desired format. I think you can do this, which I actually think I do in mine. Let me check. No, I don't actually do it in mine, but I could have. But we will use default format selection. After that, we are going to set the present mode. All right, so the present mode is basically whether or not we are going to be vsynced. Yeah, so FIFO is a hard vsync. If you want to render more faster than this, you can also change it to mailbox, and I'll show you mailbox KHR, which will not be vsynced, and there's other modes, but those are the two main ones. But we'll get to that eventually, probably. Set desired extent. All right. Set desired extent. So this is going to be the window size. Window extent dot width and window extent dot height. Now we don't have those at the moment, but we can get them in a minute. So build dot value. So we need to get these window extents. This is, again, something that we will need to get from our window itself, which tells us we need to go here, and we are going to need to get our window extents. So what we're going to do here is we're going to include the tuple header, and we're going to actually return a pair, which is going to be our width and height. So we are going to say virtual standard pair, and they're both going to be integers because I don't think we need anything else. And we will get window extents. And again, we will copy this over. We will go into our multi-platform window. We will copy this, put an override on there. We will define this function. We will move this up to be where it belongs. And then we can define this. So to get the extents, it's fairly easy to do. What we're going to do is we're going to first define a width and height. We are going to call glfw get frame buffer size, and we are going to say it's for a window, and it's and width and height, and then we are going to return a pair, which is going to be, I don't think I can do this. I have only width height. No, can't do that, but we can do tie with height. Can I do that? Oh, I think I can do this, can't I? With height. Yeah, I can do this. All right. So with that out of the way, what that will do is that we can now go inside here and we can get the window width and height. So we can say auto width height equal service locator get window extents. And here we will actually just call it width and height. And there we go. Now that will get our frame buffer size, which will create the images of the right size. So now that that's built, let's start creating everything. So first things first, we will need to store the swap chain and all its related images. And this is what makes it so much simpler. Now we can just say swapchain equal VKB swapchain dot swapchain, swapchain images equal VKB swapchain dot get images dot value, and swapchain image views equal VKB swapchain dot get image views dot value, and swapchain image format equal VKB swapchain dot get dot image format. And look how simple that was to create our swap chain. Now that that's all done, we need to clean up all of our resources. So I believe if we run this should work fine. Hit play. And you'll see bad anycast. Okay, so first things first, we know we're getting a bad anycast, so let's see what the problem is. Awesome. E dot what? How easy? What great information. Let's put an abort here. Not an abort. Let's put a breakpoint here and see what's causing the bad anycast. It's fine. Allocation callback, null pointer. Okay, because it's a null pointer, it can't cast it. So what we need to do here, since it's a null pointer, we can get rid of some of these now. We can grab this because it's standard any dot has value. Has value. If it has a value, do that. Otherwise, null pointer. And we should probably do the same thing here. And otherwise, null pointer. And what we will do is if out surface equal null pointer or vk instance equal a null handle, double or, we will throw a runtime error saying must provide both a surface and an instance. Okay, that's fine. Now let's try that again. See what happens. Will it abort this time? It still aborts. Still gives me a bad anycast. Okay. So can I do this then? If I go into my render. Now this is probably just a quick fix. May cause errors. Invalid layer may cause errors. Okay. Abort. Now what's the problem now? Where do I set my surface? And surface. Right. Oh, I'm dumb. I'm a dum-dum. Dummy dum-dum. So this is expected for the surface to be null pointer. Let's try that now. Window not equal null. Assertion. What? It says the window is open window equal glfw create window. So maybe, did I do this in the wrong order? No, it provides the renderer after the window. Oh, I see. Wait, where's open window? Open window is here. So what I actually want to do, initialize services. So I could we can do it like this for now. This will probably be okay. No? Surface not equal null. Okay, so that's getting closer. So it says surface not equal null here. Let's take this off. Hey, it worked. Okay. That did the thing. All right. So that's the errors fixed. So the allocation callbacks it might be null. So what you want to do is just not pass it in. All right. So what we're doing here is we check in our arguments. We check to see whether or not it has a value. If it doesn't have a value, it sets it to null pointer, which is what we wanted anyway. But if we want to pass in some allocation callbacks, we can do so using this function. Pass in the instance, and we get the surface here. And we can let's provide an instance. Then we create the surface. We pass it back to our renderer, and we create a device based on it, and we build a swap chain on top of it. Now all of that's being called, and none of that is throwing any errors. Now when I close the game here, you'll notice that there was no errors. That's because the validation layers, they work on everything after this point, I believe. Up to and including the... let's just see. So what we need to do now is actually clean up all of these things on destruction, on close, when we close our game. So if we look at our renderer right now, we have a shutdown function, but it's not being called anywhere. So we will add it to here, and we'll make it in the opposite order. So we're going to shut down our renderer here, and we will make a static inline void shutdown render. And then we will say if render actually we can render shutdown, and then we will just call render.reset. Render. I like doing it like this. If not render return. Render shutdown, render equal null pointer. There's no point in doing that because we're shutting down anyway, but might as well. So we're shutting down the render, we're shutting down the window, and that will make it so we call our shutdown function. All right, so in our shutdown function, what we are going to do is we are going to destroy a few things. So the first thing we're going to destroy we'll start at the end just so we can see if we can trigger some validation layers. So First thing we're going to destroy is we're going to destroy the device null pointer, and then we are going to destroy the surface, vk destroy surface, not that, instance surface null pointer. Then we are going to destroy the debug utilities messenger. So vkb destroy debug utility messenger, and then instance debug messenger. And then we are going to destroy the instance, vk destroy instance null pointer. And that's everything we need. So now I believe that it should throw a bunch of validation errors saying that we're not destroying our swap chain or our images when we're shutting down. So let's play that, assuming I didn't make any mistakes again. Okay, so it ran. When I close this, you can see now we get a bunch of validation errors. And this is why we enabled the validation layers inside our use default debug messenger. That's what this does, and request validation layer is true. So what this does is it will say that the image view has not been destroyed, the image view has not been destroyed, image view, and all of that stuff, right? So we are going to add those at the beginning. So we are first going to destroy our swap chain, vk destroy swap chain. It'll be device, swap chain, and null pointer. Then we are going to destroy each one of the image views one by one. So we can just do for auto image view in swap chain image views. And then we're going to vk destroy swap chain, destroy image view, device, image view, null pointer. And now, if we run this, we should no longer get any validation errors. There we go. All good. And when we close this, no validation errors. Okay, so now that we have our swap chain created and we have all of our Vulkan stuff started, what we need to do is set up our command pool for sending Vulkan commands, and we need to set up all of our queues, and yeah, that'll be the next step. So again, next step, we will, as usual, go into our Vulkan renderer and add what we need. So again, we are going to create a new section here, command pools and queues. So what we're going to do is we're going to, keep track of our graphics queue, vk queue, and it's going to be our graphics queue. And this is where we're going to be submitting all of our Vulkan commands to. And we are going to keep track of the index of that graphics queue on our device. So graphics queue family. We are also going to create a command pool for holding all of our command buffers into which we submit our commands. So we create our command pool. We will call it command pool. And we will create our main command buffer, vk command buffer, main command buffer. And then we need a function which will be void create commands. We will generate that function and we will call it after our create swap chain, create commands. Now in our create commands, what we will do is before that, we will actually go up to our init core and we are going to save off a couple more things. So at this point, we already have the graphics queue and the graphics queue family. So we do graphics queue equal vkb device.get queue, and then we do vkb queue type graphics, and then dot value. And we will grab our graphics queue family equal vkb device dot get queue index vkb queue type graphics dot value. Now we need to create our command pool. So we'll go into our create commands, and inside here we will create the pool. So it'll be vk command pool create info. Now, one thing you're going to see, I'll show you a difference between the way I write the code and the way you'll see it in tutorials. You'll see a lot of times you'll see the command pool equal empty struct, and then you're going to see like command pool dot s type, and then it'll be vk structure type command pool create info. Now, I find that this is too verbose, and I like following this type of style where we have our initializers in line and no equal. So this is how you'll see me initialize stuff in general, especially the create structures. Any Vulkan structures usually have an S type, and you'll usually see me do it like this. So then you'll also see that a lot of times they'll do this and they'll put a pnext equal null pointer. It defaults to that, so I will usually omit the pnext, which is for extensions, extensions, I believe. All right, so now we need to tell it which command pool, which graphics queue it needs to be on. So dot queue family index equal graphics queue family. And finally, what we want to do is we need to allow for resetting the individual command buffers so that we can reuse command buffers. So command pool create info dot flags equal vk command pool create reset command buffer bit. And finally, we will create the actual pool. So this is where we use our macro that we defined earlier in our vk utilities, our vk check. So this is where we are going to call vk check and vk create command pool device. Oops, Control P, and then the create info. So end command pool create info. Allocator, which is pretty much always going to be null pointer in our use case, and the command pool itself, which will be command pool, and it should be a pointer to command pool. Now what's wrong? What's wrong with this? I see the error. Here I have one too many shoots. That should fix it. Yeah, that fixed it. So if you followed along too closely, you might have made that mistake, but you probably didn't. There we go. So what that'll do is it'll create a command pool and it will abort the application if it doesn't work. Now, from this command pool, we want to allocate a command buffer. And the command buffer is where we will actually be submitting our Vulkan commands. So all of our Vulkan commands are prefixed with the vk command prefix. So we need to create our command buffer and submit our vk commands to our command buffers. So let's create our command buffer now. So we will create the default command buffer that we'll use for rendering, vk command buffer allocate info, and command buffer allocate info. I like being verbose, and it auto-generates it for me, so it's not a big deal. Again, vk structure type, command buffer allocate info. And this will have so we will tell it which command pool it is. command buffer and command pool equal, and this will be the command pool. We will allocate, we will allocate one command buffer right now. So command buffer count equal 1. And then we tell it what level of command buffer we want to create, which is going to be primary, vk command buffer level primary. Now, for the most part, you're going to be creating primary command buffers. Secondary command buffer is, I believe, if you want to, like, you have a main command buffer, and within that command buffer, you want to run more command buffers in between, or something like that. I'm not entirely sure. Like I said, I'm still new to Vulkan as well, so we'll stick with the primary for now, and maybe we'll explore later. And finally, with all that done, we want to allocate the command buffer, and we'll use the bkcheck macro. So we give it our device, we give it our command buffer allocate info, we give it our command buffers, and since we're only allocating one, we just give it our main command buffer. Now, if our main command buffer, if we want to allocate 2, like if we had 2 here, this would have to be an array of some kind. So you could either create a vector and give it the vector, or create an array or whatever, but that's how we do it. So this is actually going to be a common operation, which we're going to have to do more than one time, creating command buffers and creating command pools. So what we're going to do, for convenience sake, is we're actually going to abstract this out into an initializer function, which we have scaffolded a spot for in here. So what we are going to do is we are going to take this and we will create some functions. So first we're going to have to create our command pool create info. So static command pool create info, and this will actually be not this. It should have a return type of vk command pool create info, and we will need to include our vulkan.h. All right, so inside here we are just going to need a couple of things. We are going to need a uint32t, q family index, and we are going to need vk command pool create flags, command pool create flags, and we will default this to nothing. And we will create one more static function, which is going to be vk command buffer allocate info, and command buffer allocate info. And what this will have, it will take a vk command pool, it will take a count, and it will take a level, and those will be defaulted. So it'll be uint32t count equal 1, and it will be vk command buffer level equal vk command buffer level primary. Now we will separate that to a new line, and let's implement these functions. Now I don't like the way CLion breaks apart these lines. I don't like at all. So it's not ridiculously long, so it's fine. So all we need to do now is we will take the code that we had in here. We'll take this. So we will actually just copy it for now. Copy that in, and we will return this. Return this. We will put Q family index there. And we will put flags equal flag. Oops. And yep, that's all we need for that. And for our next one, we will take this one. What's that? Our initializers. Paste it in. We'll say we want pool, we want count, and we want level, and then we want to return our command buffer allocate pool. So with that done, we can then go inside here and we can say equal Vulkan initializers command buffer out create info, and we queue family index, which is going to be graphics queue family, and flags will be VK buffer command will create reset buffer bit. And we actually deleted a line that I didn't want to delete, so let's go back, just grab that back and put that back in. All right, and then here it's going to be a similar operation. Equal Vulkan initializers command pool allocate in pool, and this one here we just need the pool. We need the command pool. And there we go. And that makes that set of code much simpler to do. Let's get rid of the slash. All right, so as before, we need to clean up what we created. Now, command buffers automatically get cleaned up if their pool is destroyed. So we just need to clean up the pool. So let's go inside here. So just a note, anytime you see a VK create, you usually want a matching VK destroy. So we will go here, VK destroy, command pool, device, command pool, null pointer. And now we can build this, and we should be able to run it, and we should not get any validation errors when we close it. Hello YouTube game, no validation errors on exit. All right. So the next thing that we need to do is we need to set up the render pass. Now, to render to a screen, you need to do one or multiple render passes. We are going to do everything in a single render pass for now. Ideally, we're going to want to do multiple in the future. But what the render pass will do is it will clear the screen, it will render everything, and then it will end, and then we'll present, and then we can present the image to the screen. And then in the future, once we have more complex stuff, you'd have a render pass for color, for specular lighting, or whatever. There are different render passes which will do different layers of the render. To do this, what we need to do is we need to do a couple of things. We need to create more objects. What we want to do is we want to create some more stuff. So I'm going to create another section here, and we're just going to call it render passes. Now these sections they're going to start breaking down at some point. At some point, they're not going to be easily separated, but at least this way we'll be able to quickly scan the code and find what we need most of the time. So what we will need is, first we're going to need a render pass. So render pass. And then we are going to need frame buffers for our render path. Std vector, std vector, vk frame buffer, and frame buffers. And then we will go up and we will create two more things. We can say void create default render pass and void create frame buffers. Now, when we get to VR, this is where a lot of our work is going to be done in these functions. So create default render pass and create frame buffers. And let's just copy these and put them inside our init function right after our create commands. Put those there, and we'll just delete these. So for our render pass, a render pass has, you give it attachments, or you define which attachments it's going to output. and I believe it's output, not input, but you give it different outputs, which it will write into. You create the render pass using those attachments. And it will also include stuff like the format of the images and stuff like that. So let's go through it, and then anything I feel needs explanation, we'll explain. So we'll go VK attachment description, color attachment. So this is our main color attachment. So we're going to do this in order. So the first thing we need is the format. So the format is going to be the same as our Swapchain image format. The samples, we're not going to use multi-sampling right now, so we are going to do VK sample count 1 bit. For our load operation, so the load operation is when the render pass begins, when it first loads. What operation is it going to do to the existing color attachment or the existing output on the frame buffer? So we do load op equals, and we want to clear the frame buffer on load. The store op is once the render pass is finished, what do we want to do with that frame buffer color data? In our case, and in most cases, you're going to want to store it, because if you don't store it, how are you going to render it? The stencil stuff is about transparency and stuff like that. We're not going to get into that right now, but we do have to define it. So we're going to stencil load up equal, and we are just going to say attachment load up don't care. And same thing for the stencil store up. We are going to do VK attachment store up don't care. Finally, when the render pass begins, we need to tell it what image format or what image layout the image should be in when the render pass begins. In our case, and in, well, not most cases, but at least in our case, we don't care. We just need it to have, we just care about what it'll look like at the end. So we are going to say VK image layout undefined, which means that we don't know and we don't care what it's going to be at the beginning. And then final layout, we want it to be in a layout suitable for presenting to the screen, which is layout present source KHR, and that's self-explanatory. It puts into the present format. Now every render pass needs at minimum one subpass, which will actually be what does the work. Now you give the color attachment to the subpass by means of a attachment reference, and yes, it's all complicated for almost no reason, but the reason you do it that way is because you can have multiple attachments, and the attachment references also give you indexes into the different things. So let me show you. So VK attachment reference, color attachment reference, dot attachment equal color attachment dot layout equal VK image layout color attachment optimal. Now what is this saying? Oh, this is 0. This needs to be 0. Yeah, so the VK attachment reference will point into a attachment array, so an array of these things, when we create the render pass. So I'll point that out in a little bit. So with that, we will create our subpass description, subpass. We pipeline bind point equals VK. So this subpass will run on the graphics pipeline. It will have one color attachment count, 1, and then we give it the attachment references, color attachment equal, and color attachment references. So just to be clear of what's going to happen here is when the render pass begins, it's going to be in an undefined format where we don't know what it is. Then it will start the render pass and begin the subpass. Once the subpass starts, it will transition to layout color attachment optimal. And then once that finishes, the render pass will end and it will transition to VK image layout present source KHR, which is Chronos. So now with the main things defined, we can now create our render pass. So we are going to VK render pass create info, and we render pass create info, and again VK structure type render pass create info. Now we need to give it its color attachments. So render pass create info dot attachment count equal 1. We have 1 attachment. We give it a reference to our color attachment. And then we connect our subpass. So render pass create info dot subpasses, subpass count equal 1, and render pass dot p subpasses equal and subpass. And then with all that done, we create our render pass with VK create render pass. Now there's these 2 functions which are newer and are probably recommended. I haven't looked into how they're used, but I imagine they look very similar. Pass create info 2. It's just got using the create info 2 structs. They look roughly the same. So anyways, we're just going to create render pass for now. So it takes a device. It takes a render pass create info. So render pass create info. It takes an allocator, which is null pointer every time in this series, and a render pass, which is render pass. And we've got ourselves a render pass. As mentioned, so just to go into go over this one more time because it's a little bit can be a little bit obtuse. So when the render pass begins, it will load the first color attachment, which will say that its initial layout is undefined. When the subpass starts, it will go to attachment 0 and transition to a color attachment optimal. And then once that's finished, it will connect to attachment 0, which is the color attachment here. That's how the indexing works. So if I put here, let's just we take an attachment reference refs, and let's say we say color attachment, and we put 2, and then we put refs. This is descriptions. That works. Oh, whoops, there. So if we did this, and we wanted to, and we had a second, so for example, eventually there's going to be a depth attachment here. So getting the depth buffer, our depth will be attachment 1, and we will have the attachments here, and the depth will be referenced as 1 here. So it'd be depth here. But that's for later. We'll see that later. But that's basically what all of this is doing. It's just being very self-referential across everything. So with our render pass created, we will now create our frame buffers. So the frame buffers are created for a specific render pass. Again, this is more stuff that we will go into later when we go into VR stuff, but For now, let's create some frame buffers. So VK frame buffer create info, and frame buffer create info, and again VK structure type frame buffer create info. So first thing we want to give it is our render pass, which is just render pass. The second thing we want to give it is the number of attachments that it has. Frame buffer dot attachments equal 1. We'll come back to this attachment in a minute. We'll come back to this. We will then give it our frame buffer width and height. Now, what we should have done up here, so up here you notice we took our width and height here and we just used it and got rid of it. Now, when we have our swap chain creative of a certain size, everything else should remain the same size. So we just want to make sure that we don't accidentally change it. Yeah, so if for some reason the window was resized and we didn't catch it, then in between these things for some reason, then calling this again might return a different value, which is not good. So what we are going to do is we're actually going to store the width and height inside here. So core Vulkan swap chain. So we'll do here. So we can do VK extent 2D window extent. And then inside here, we will do window dot width equal width, window extent dot height equal height. And then with that done, we can then reuse down here, and we want to give it the width and height here. So frame buffer create width equal window extent dot width, frame buffer create info dot height equal window extent dot height. And then again, you can have different layers on your different images. I don't quite know exactly how that works, to be honest. So for now, we'll put it at 1 because there's always at least one image layer. I think it's for like you can make like cube maps and stuff like that, and I think that's what that's for. So we want to then get how many images are in our swap chain. So what we're going to do is do const uint 32t swap chain image count equal swap chain images dot size. And remember up here when we create our swap chain, it generated images for us. Now I believe it probably created a single back buffer. It's probably going to be 2, but might be more. I don't know. Look it up in Vulkan Bootstrap VKB. It'll probably tell you. So then once we have that, we want to resize our frame buffers, or we want to initialize our frame buffers. And I believe swap chain image count. This is what we want to do. So if you look here, inside here, we created our swap chain, our frame buffers. We're actually going to initialize it as an empty, and actually we're going to initialize, can I do that? Yeah. So we're going to initialize it as 2, because I think that's the number we're going to get. Actually, you know what? Let's just see what it gives us. So let's go here. Let's go inside here, and let's just see what it gives us. I think it'll default to 2. 2 is a sane default. Swap chain images. This swap chain images size 3. So it's a double back buffer. Okay. So since it's defaulting to 3, what we're going to do is we're going to default this to 3 as well. So what that'll do is just that if for some reason it's not 3, it will most likely be 2. I doubt it's going to go higher. And then it will shrink it. And I think shrinking is a lot cheaper than growing, I would imagine, because you're just moving a stack, I would imagine. I would imagine it's faster. So that's what we're going to do. We're going to resize it to the Swapchain image count. And then we are going to create our frame buffers for each image. So we're going to for int I equal 0, I smaller than Swapchain image count, I plus plus. And then we are going to create the attachment for the frame buffer. So frame buffer create info dot p attachments equal and end Swapchain image views. Yeah, I. All right, so let's just finish this. So then vk check vk create frame buffer device and frame buffer create info null pointer and end frame buffers I mentioned earlier we'd come back to this. So in our frame buffer create info, we have to attach an image view to which the frame buffer will be attached and read from. So this is how we create that connection, is by p attachments here, and there is one attachment. You can create multiple attachments for frame buffer. I don't know why. I imagine it makes sense to be able to do it, but we are only going to do one for now. The other thing you'll notice is that we can actually, all we're doing is we're creating frame buffers using the same create info object, but in a loop, and just replacing a single value. All of these create info structs, that's exactly what they are. They're just structs of data. So if you're creating a bunch of stuff and there's no changes in between them, you don't have, or almost no changes in between them, you don't need to create a new frame buffer create info object every single time. You can just reuse it and replace the fields that you're interested in. Makes sense? All right, so that's our frame buffers created, and that only leaves finally the last step of this part, and that's cleaning up after ourselves. So you notice here we have a vk create here and a vk create here. So we want to destroy those things, and as usual, we'll usually do that in reverse order. So what we're gonna do is for auto frame buffer in frame buffers vk destroy frame buffer device frame buffer null pointer, and then we want to destroy the render pass. So vk destroy render pass device render pass null pointer. So let's hit play on that, and in theory we shouldn't get any validation errors. It should run. So there's no errors so far, and when we close it, no validation errors. So that's everything for frame buffers and render pass. And finally, what we are going to do is we are finally going to render our we're going to clear the screen to a color. So a few more things we're going to need. We are going to need some synchronization objects. So synchronization objects. So we are going to need two semaphores. We're going to need vk semaphore. We are going to need a present semaphore and a render semaphore. And then we're going to need one fence, which is a render fence. And then we are going to need a create sync structures. and let's generate that definition. So these sync structures are used to make sure that we are not presenting an image that is being rendered to, and we're not rendering to an image that is being presented. We also use the render fence to make sure that the rendering itself, the render loop, has completed, and that everything before the fence gets executed and finished before anything after the fence. That's a basic explanation, and we'll go through and you'll see how they're used. So the first thing we're going to do is actually create them using our create sync structures function. So these are simple enough to create. vk create vk fence create info, fence create info, and then vk structure type fence create info. So the fence that we're creating is the render fence, and when the render fence is signaled, it means that we are ready to render a new frame. Now, if we just create the fence with just this structure here, it would create the fence in an unsignaled state, which would actually block our render loop from ever running, because basically we're telling it it's not ready to render a frame yet. So if we take the fence create info and add a flag to it, vk fence create signal bit, this tells it that the fence is ready or signaled on creation. So since we're using it to tell us whether or not we're ready to render a frame, the first time we use it, the first time we render a frame, it will say we're ready to render a frame immediately. Okay, and with that we will create our fence, vk check, vk fence, create fence, device, and fence create info, null pointer, and render fence. Our semaphores are actually even simpler. They actually don't need any flags at all. So we can say semaphore create info, vk structure type, semaphore create info, and then we can just vk check, vk create semaphore, device, and semaphore create info, null pointer, and end present semaphore. And we can just copy paste that and change this to render semaphore. And that's all we need to do for creating our sync structures. And again, we'll go up and we'll make sure that this is being called from our init function. Okay, so we've created the sync structures. Now for our draw loop. So we've already basically got the draw loop. So if you remember in our game.cpp, in our run loop, while running, we've actually got this get renderer render frame. Now that's actually our draw loop. So we don't need any other functions. It should work as is. So this is where we're going to render our frame. So first we need to wait until, like as I told you, we're going to use our fence to wait until the last frame is finished rendering, or the last render loop is finished rendering. So we're going to do a vk check, and we're going to do vk wait for fences, and it's going to be device. We're going to wait for one fence, and we are going to wait for our render fence. We're going to wait for all fences, because we can wait for multiple fences, and then we give it a timeout, and we're going to give it a timeout of 1 second. And I don't want to count zeros, but 1 second is this many zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros. So 10 digits is 1 second. So what is that, like nanoseconds? Yeah, it's a nanosecond. So this is a nanosecond. And then once we've finished waiting for fences, we need to reset the fence. So when at this point, the fence is considered signaled. So let's say it has a flag of 1, right? So when it is 1, wait for fences, it's waiting for the fence to become 1. And once we're done, we want to set it back to 0 so that it blocks on the next call. So if we go vk check, vk reset fences, device 1, render fence. And this sets it to 0. Basically, it might be the opposite. It might be something more complicated, but in essence, that's what it's doing. Here it becomes 1 and continues, and then here we set it to 0 so that it doesn't, so that if we call wait for fences again here, and we don't do anything in the middle, it's going to block because we're not doing anything there. So, next thing we want to do is we want to get the next image in our swap chain. So the next thing we need to do is we need to acquire the index of the next image in our swap chain. So we're going to take something to an image index to keep that index. And then we are going to acquire the next image. So it's function vk acquire next image khr. It's going to be device on our swap chain. The timeout is going to be 1 second, which again is in nanoseconds. So we're just going to paste that. Damn it, I hate the semaphore, we're going to give it our present semaphore. This is just to make sure that we can sync it with just to make sure that we have image ready to present, basically. There's going to be no fence. And we are going to put it into Swapchain image index. At this point, we know that since we've waited for this fence and we've waited for this semaphore, we know that our main command buffer is done processing its command. So we can actually reset the command buffer. So we will do that, vk check, vk reset command buffer, and main command buffer. And what's this? And flags, no flags. That's what that'll do. Now I'm omitting comments here. If you want to see the comments on a lot of these lines of code, again, vkguide.dev, source, go see it. It goes much more in depth than what I'm doing. I'm trying to show you, just give you a basic explanation. So now we're going to, I like this convention is we're just going to rename our command buffer, or we're going to store a handle as command just to make it easier to type, because we're going to type it quite a bit. And then we are going to begin our command buffer, or our begin command buffer, whatever. So we want to vk command buffer begin info, and we will do command vk structure type command buffer begin info, and we don't need to give it anything except for a single flag, which so in a fully optimized Vulkan application, there are going to be instances where you're going to be able to record a set of commands and only one time, and then reuse that same command buffer over and over and over again in subsequent frames or whatever, so that you can save that CPU time actually recording those command buffers. So in context of a game, it's not necessarily going to happen an extreme amount of times, but for example, one thing I can think of is in the future, we are going to have as I showed you before, we're going to be rendering our eye textures to the window instead of rendering directly to it. Now, when you do that, you'd probably be able to record the command buffers for setting up the companion windows only one time, and then submit that same command buffer over and over again. That's my understanding of the next flag, the flag we're going to put in here. So if we put it our begin info flags, VK, command buffer, usage, one time submit. So this says that we can only submit the command buffer once before calling a reset on it. So we need to reset our command buffer. This is what this reset command buffer does. We need to reset our command buffer before we can submit this command buffer a second time. That's what that flag does. And then with all of that out of the way, we can call VK check, VK begin command buffer, command, and begin info. Now we can start doing some fancy things. We are going to keep a reference at this point to the frame number that we're on, like absolute frame number. And this is just for our own reason. So we'll put it here, and we'll just mark it as, we'll put a to-do here, temporary frame number, which wasn't so temporary inside my application, but we're gonna do it here. So we're gonna say int, uint, so we'll make it a very big integer, uint64t, frame number 0. And we'll initialize it as 0. And then inside our renderer, we can go back here and we can do this. So we are now going to clear the screen to a color, which has been the goal of this entire lesson. At this point, it might be a couple of hours. I'm sorry. So VK clear value. Now, if we look at VK clear value, it's got a VK clear color and a VK depth stencil. So we are going to just do the color, and it's going to be 4 floats. So it's going to be here, and we're going to do color equal, and it's going to be 4 floats, which is going to be, we want to get the flash color. So we're going to do float flash color equal the absolute of the sign of float frame number divided by 120f. Now I want to actually rename frame number because it's a private variable, and the convention we have been using is having an underscore. So let's put that there. All right, we have the clear value, and then the color itself, we are going to put 0.f, flash color, and 1.f. That'll be our clear color. Now we can actually begin the render pass. So VK render pass begin info, render pass begin info, and VK structure type render pass begin info. And then what do we need? We want to give it the render pass, so we will give it our render pass equal render pass. Then we will need to give it an offset, so we will go render pass begin info dot render area equals, and then we're going to do this offset equal dot x equal 0 dot y equal 0. And here we will give it a comma and dot extent equal window extent. And then we will do render pass begin info dot frame buffer. So we want to give it the frame buffer that we're working with, which is going to be the frame buffers, and it's going to take the Swapchain image index that we acquired earlier. That's what we do there. Now, we then want to connect the clear values to our render pass. So connect clear values. So render pass begin info dot clear value count equal 1, render pass begin info dot p clear values equal end clear value. And then finally, once we've got all of that defined, vcast render pass begin render pass command begin vk command begin render pass. Sorry. So now that we began our command buffer here, we now submit everything as a vk command, as I mentioned before, as a vk command begin render pass it the command buffer, the render pass begin info, and the subpass contents, and we're going to say vk subpass contents inline, which I believe just means that we are rendering directly to the subpass attachments. I believe that's what that means. So you'll notice here, we give it a clear value count and we give it a clear values. So if you remember when we created our render pass, let's find our render pass, create render pass. So when we created our render pass, we told it that on load that we would clear the color attachment, and that the color attachment is attachment 0, and that we gave it to our render pass when we created it. So what this is saying here is we have one clear value count and its clear value. The first, the order of this array, because p clear values is an array, the order of this array, I believe, needs to match the order of the array we gave in our attachments here. So when we have our depth attachment for clearing the depth buffer, we're going to have a second attachment at attachment 1. We're going to attach it here in the same order. Then in our render, we are going to have another clear value, which is going to use the, if you look here, I showed you there's also the depth stencil, which will have the depth stencil clear, and that will be the second value in our array and will clear the second color attachment that we give the render pass. I believe that all that information is correct. If anyone who knows Vulkan better than me is still watching this at this point, then let me know if I'm wrong. All right, so we've begun our render pass, and finally, that we're not doing any actual draw calls, but if we were making any draw calls, they would go here. But all we're going to do is vk command end render pass command, and we are going to end the command buffer, vk check, vk end command buffer command. And then finally, since we've finished recording our command buffer, we are going to submit it to the graphics card for execution. So we want to wait on the present semaphore, as that semaphore is signaled when the swap chain is ready, and we will want to signal the render semaphore once the rendering is finished. So we can vk submit info submit, and again vk structure type submit info. So we want to make sure that we wait on reaching the color attachment output stage before we start rendering. So vk pipeline stage color attachment output bit, and that should be an equal. And we want to, at that point, we want to also wait until we've reached the wait stage. First and wait stage. We also want to wait on the semaphore, the present semaphore, to be signaled so that we know that the swap chain is ready to render, I believe is what this is. Again, this is all complicated, so I'm trying to vocalize what all this is, even if I don't fully understand it. So wait semaphores and present semaphore and remove this. Once we finish our command buffer and we finish rendering, wait destination stage mask. I think that's right. Anyways, once we finish rendering, we want to signal the render semaphore, signal semaphore count, to indicate that we are ready to render a new render to the screen. And then we will command buffer count, and we are only going to submit a single command buffer. And with our submit info struct created, what we will do is we will actually submit the queue, and we will have it signal our render fence when it's done rendering, so that we can signal that we're ready to start rendering another frame. At the beginning here, we wait for the fence. So vk check, vk queue submit. We submit on our graphics queue. We submit one. We submit our submit info, and we signal this fence. So once the commands are submitted, what we're going to do is we're then going to present the image to the screen once the rendering is complete. So we know the rendering is complete when the render semaphore is signaled. So what we will do is vk present info, vk structure type present info khr. Then we give it our swapchain dot swapchain count equal 1, p swapchains equal swapchain, and that should be a pointer. Then we tell it to wait on our render semaphore, so present info dot wait semaphore count is 1, present info dot p wait semaphores equal and render semaphore, and we tell it which index to present to, which swap chain index to present to the window. So we give it present info dot p image indices equal and swap chain image index. So I believe this we could technically present multiple indices to the screen at once. I think that's what this says. I don't know why this is a pointer, but that's what we're doing here. Well, maybe we'll find out why it's a pointer later. And then when we have that completely filled out, we will call vk check, and then vk queue present khr. Again, we will present it on the graphics queue and present info. And now with that done, we should have a flashing blue screen. That should be everything we need. Other than cleaning some stuff up, but we'll see that after. So we'll press play and hopefully we get what we are looking for. We do not. So why don't we get what we want? Because we are not frame number ++. Now let's play that. That should give us what we want. Yes, and that's exactly what we want. And now we have a flashing blue screen and a working technically renderer. Now, if you can now officially follow some other guides on how to actually render some Vulkan objects and Vulkan structures. Now, what we're going to do first is, you'll notice here we've got some validation errors on when we leave. So we've got all submitted commands that refer to Framebuffers must have completed execution. So one thing, it's going to be kind of a cheat that we're going to do for now. We can't destroy stuff until command buffers are done, and we can wait for the device to become idle before we do that. So we can wait device wait idle and device. That'll make sure that our device is idle before we start destroying stuff. So let's play that again. And still getting our flashing blue screen. When you close that, we still got some error. So what do we got? We didn't destroy our semaphore, and we didn't destroy our fences. So again, we do everything in reverse order. So here we will vk destroy fence, device, render fence, and null pointer, and vk destroy semaphore, device, present semaphore, null pointer, and let's just copy paste that. And this will be render semaphore. And now let's just change the color just so I can show you that this is indeed, let's put flash color, and let's just put flash color here too. And now we should get a different color. RGB, what is that? Purple? No, turquoise. And there we go. We got a different blue. And if we close this, no more validation errors. So I'm glad if you stuck with me for this journey on implementing a Vulkan renderer inside our game engine. We will continue on this journey either next video or a video soon. I know this is nothing exciting is happening yet. We don't even have a triangle, but we are close to having a triangle, my friends. We are close indeed to having a triangle. We're actually very close. So I hope you enjoyed this introduction to Vulkan. It was fun doing all of this again. It actually is cleaner so far than my own project, and I understand it more now. So with that done, thanks for watching. Hit subscribe, like, all that crap, and I'll see you next time.